Okay, for part 3, we're going to be looking at the Doppler effect, bow waves, shock waves, and the sonic boom. Okay, the Doppler effect we use all the time in science and in weather prediction, and also policemen use it. So the Doppler effect is when you have a source of sound or motion um, that is in motion. Okay, so a source of sound is moving, or the observer of a sound is moving. And it doesn't have to just be a sound, it could be a type of electromagnetic wave, like light, um, or in the case of a speed gun for a police car, it could be a microwave. So anyway, or a radio wave. So anyway, something is moving, the source or the observer. So the idea is that Christian Doppler, who lived in 1803 to 1853, he was an interesting fellow. He was kind of like Newton in that Newton should have been a farmer, Christian should have been a stone carver because that was his family's business. But Christian was kind of weak and not very strong, and he was sickly, so his parents said, oh, let him go to college. So anyway, so he went off to college and became a professor eventually. Now, he was living during the time when trains were just becoming popular, and he noticed this interesting and unexplained phenomena at the time, that as a train approaches, the whistle has a higher pitch. So the train's coming toward you, it's going, and then it passes by and the sound becomes lower. So the train's going, ooh. So if you've ever heard that, which every child knows, because that sound is the sound that race cars make. Because a race car is coming towards the microphone of a recording or towards the position where you're sitting, and it's sounding like, and then it passes you by and it goes, right? That's the Doppler effect. So every kid knows what cars sound like. They go, zoom, zoom, zoom. They're trying to do the Doppler effect. Okay, so anyway, Christian figured out the math on this, and that the train whistle was the moving source of sound, and the observer was standing still. But they needed a way to test it, and they didn't have any way to actually record sound in those days. There were no tape recorders yet. There was no way to analyze the frequency, except using humans. So what he and a friend did, um, they hired, they scraped together enough money to hire trumpet players who sat on a railroad flat car, and they hired the train to drive past at various speeds a platform on which there were groups of musicians who had perfect pitch. So perfect pitch is when you can identify a sound just by hearing it. You can say, ah, that's a B, or that's an A flat, or that's a C. Um, so these perfect pitch musicians would sit there, and the train would move by at various speeds with the trumpet players playing. You know, they would all be playing B, and the musicians with perfect pitch would say, ah, now it's B flat, or now it's B sharp. And so they would say what was happening, and then Christian would try to figure out if that fitted his equations. So anyway, so that experiment actually went on for 2 days. And so it's one of the coolest experiments in science, that they use live musicians to test out this hypothesis. Okay, so anyway, it confirmed Doppler that he was right in his mathematics. Okay, so what's going on? So if you can imagine, we've got a bug that's singing, going, ah, and the waves are moving out in all directions, and they're all the same, right? So if you imagine these things are the wave fronts, so they're like the peaks or something. I'm not drawing this very well. Anyway, so the peaks, and so they're moving out in all directions evenly. Okay, so what happens is for the observers, A and B here, their ears are getting hit by the sounds that are coming at them at the same time, right? Because it will take the same amount of time to travel this one wavelength of distance, okay, in each case. So for A and the B, they will hear the same sound because the pulses of sound are hitting their eardrum with the same period in between. So they will hear the same frequency or pitch. But what happens if the bug starts to move? So in this case, the bug is moving to the right, going 1, 2, 3, 4. He's singing, ah! But what happens is that the wave fronts are getting piled up on each other. So now the distance between them and the time between them is shorter. And so they're hitting the ear of B with less time between them. So what B interprets it as is a higher pitch. So B hears, ah! And for A, because the waves have been basically trying to move away from him, then there's a greater distance now and a greater time between the wave fronts hitting A's ear. And so what happens is that A hears a lower pitch. Ooh. So anyway, so you've got higher pitch and lower pitch, and the bug is singing. Anyway, so yes, so you have different frequencies being heard. And basically, when the source of sound is moving toward, then that's going to be a higher pitch. When the source of sound is moving away, then that is going to be a lower pitch. Okay, so higher pitch, lower pitch is what's heard. Frequency. Okay, so anyway, so this happens all the time around us, especially for something moving fast. That's when we notice it, because the faster something goes, then the greater the change is in the pitch. So when you've got a fire engine, next time you have to pull over because there's an ambulance coming by or a fire engine, listen to the sound as it comes towards you. It might be going, and then as it passes by, it's going, it's got a lower pitch, right? So it comes towards you, and the pitch is high, moves away from you, the pitch is lower. Now, it turns out that, so toward is higher, away is lower. And it doesn't really matter, as it turns out, if the source is moving or the observer, because it could be you're driving towards, you're not supposed to pass ambulances or anything. But if you were able to pass an ambulance with a screaming siren, as you move towards it, you would hear a higher pitch. As you moved away from it, you would hear a lower pitch. Okay. Now, what if you're being chased by a police car? Same thing, right? If you pull over, you will hear the Doppler effect as it changes its pitch. But if you stayed the same distance away from the police car, so you were moving at the same speed, then you would hear the real frequency. Okay, so, but don't do that. No car chases. Now, we find this extremely useful. What happens is that radar sites are all over the country, and they send out radio waves that hit raindrops and echo back. When they echo back, they have gained a little bit of motion from the raindrops that are moving sources. And so because of that, it changes the frequency a little bit. And that's how they catch your car too. The frequency that goes out hits your car, and it changes a little bit because your car is in motion. And the bigger the change, then the policeman knows you're going at a bigger speed. Okay. Now, this was the horrible tornado that hit Moore, Oklahoma. One thing is these tornadoes often have what's called a hook echo in the back. So if you're watching on TV or something and they say, well, warning, there's a tornado, that's what they're looking at. That particular shape is where the tornado is forming. And of course, we use this all the time to warn people about things like that, so we can measure hurricanes. The Doppler effect is also used by astronomers when they're looking at the light of stars. And so a red shift versus a blue shift is a description of what's happening when the star is moving away, and the frequencies get larger. And so red has a longer wavelength, and that would be a lower frequency. And the blue or violet end is a higher frequency. And what happens is the star moving away, that light will change its pattern. So this pattern is called a spectrum. So this is the spectrum of an unshifted star. So what it is you're looking at all the colors of light being produced, but they're little lines because atoms will absorb some of the light energy. So that's called a spectral pattern. And we'll learn more about that in a future chapter. So anyway, so what happens here is that a red shift means that these lines have moved a little bit over. And so you can see how this one has moved a little bit to the right. And so because of that, that would be towards the lower end of the frequency, the red end of the frequency. So that indicates a star that's moving away. Okay, because all of these lines have moved a little bit over from their position up above. And a blue shift is when the star is moving toward our planet. And so in that case, all the lines shift a little bit to the right. They don't have to become blue. I'm sorry, towards the left here, towards the blue end of the spectrum. They don't have to become blue. They just have to shift a little bit that direction. And here's a formula for it because someone asked for it last term. For the Doppler effect, we don't have to use this formula. But basically, it's saying your initial frequency results in a new frequency depending on the velocity of the source or the velocity of the observer. Okay, and in a cluster of galaxies here, also using the Doppler effect, these have been shifted towards the red end. They are moving away from us. Okay, now what happens if the source of sound moves so fast that they can move at the same speed as the waves? So if this was a sound wave, that would mean 340 meters per second, which is about 780 miles per hour. So it's very fast. So what if you could move that fast? And so we've heard about people breaking the sound barrier in jet planes, right? Mach 1 and Mach 2 and that sort of thing. That's what goes on. But this also happens in water. Now, water waves aren't as fast as sound waves. So a boat can easily go faster than the waves that it's producing. Okay, and that creates what's called a bow wave. So this is sort of showing what happens if the bug was singing, but as it was singing, it was moving also. And so if I sang, and then I moved at the same speed as my voice, then what would happen is my air that I'm expelling right here, my sound energy, would get built up right in front of my face because it can never get away from it. I'm moving the same speed. So I would keep singing, and it would keep building up. So that's what's called a bow wave. And you can see how this bug here has all this wave energy built up in front of it. Okay, so this would be a bug swimming or singing at the speed equal to the wave speed. And so here's a bow wave on a submarine. And so you can see this mound of waves in front of the submarine. Okay, and maybe you can also see a little dolphin here because dolphins love to ride in front of ships because they can just play and have a free ride on the bow wave. It's one of those continuous surf pools that people like where the wave stays forever. So dolphins love that idea too. So they will come towards a ship just to play in the bow wave. Now, what would happen if you could go faster than the speed of the wave? Well, that results in a shape like this, where the wave builds up on the sides in a V shape. And that's called a Mach cone. And it's high pressure wave buildup in this V. And so here's a boat. You can see this boat, and it's jumping over its own waves. So you can see the old waves that it's left behind, but that has built up in this V shape on either side. Okay, so boats can do this. They can go faster than the speed of the waves. And the thing is, so what happens is that you get a velocity less than the velocity of the wave. That's just the normal Doppler effect. When it piles up in front, because it's equaling the speed of the wave, I think that's just called a bow wave. When you start to exceed the velocity, then you get your Mach cone shape, okay, where it builds up on either side in a V shape. The faster you go, the smaller this angle. Right? So the angle changes, and you can tell whether the boat is going much faster. So like this boat, you can see it's going much faster than the speed of the wave. Okay, now when a bullet goes through the air, it is moving faster than the speed of sound. They say that you will not hear the bullet that kills you if it goes directly into your head, um, because because it does fly faster than the speed of sound itself. So if you hear a bullet passing you, that's good. That means you're probably still alive to hear it. But the one that kills you, you won't hear. Anyways, that's kind of grim. But here we have a bullet that crashed through some plywood with a bunch of debris, and we can see that it has 2 Mach cones of air pressure. And so this is the high pressure wave here. And this is actually a low pressure as air falls in behind the bullet. So you've got high and low air pressure cones, Mach cones following. And that's what we also call a shock wave. So these can shatter glass. Although, and so that's one reason that people don't like airplanes that move faster than the speed of sound to fly over cities, is they fear that windows will get broken and people have heart attacks. If you've never heard a sonic boom, it's really cool because it's boom all of a sudden, out of nowhere. I used to live in Kansas, Wichita, when I was a kid. And that's where a lot of aircraft manufacturers are, like Boeing. That's where they started out. And so they would test their planes frequently around there, so you would hear it. Or if you live near an air base, then you would get to hear the boom. But yeah, Chicago has banned it from the lake water show, which is too bad because, yeah, it used to zoom by in Chicago and make a big boom as the jets would fly in the air show. Anyway, so when they move faster than the speed of sound, which the speed of sound is called the sound barrier. And why was that? Well, it's because as the plane would approach that speed, there would be a lot of vibrations that would get set up, and you have to push through that. There are reasons for that, which I'm not going to go into. But anyway, so what would happen is that people had to build planes sturdy enough to make it through that part. And then once they actually were able to go past the speed of sound, then they were leaving all that vibration behind. So anyway, so this sonic boom trails behind the plane as long as it moves faster than sound. So we're going to look at that a little more. Meanwhile, this plane has this little cloud following it. That's because the pressure wave here, is actually squeezing water out of the air. So it makes a little cloud under the right atmospheric conditions. So here's the shock wave Mach cone that is following this airplane. And so it is a cone shape spreading out behind it, intersects the ground at various points. And so what would happen is if you were at one of those points, then you would start to hear that sonic boom. And there is the high pressure and then a low pressure part. So your eardrum would get pushed in and then pulled out. And that is what causes that boom in your ear. And the idea is that this boom doesn't hit everybody at the same time because your heads are all in different places usually. So what would happen is the cone would have to pass over your head. So you can see C here has heard the boom and he's holding his ears. And B is just now experiencing the boom. And A hasn't yet experienced the boom because it's still coming towards it. Now he might be able to look up and see the plane because light moves faster than sound, but he doesn't hear it yet till it hits his head. And actually that's one of the cool things at air shows is they will have you watching a biplane doing tricks or something. And meanwhile, jets are circling around and then they come over the crowd and you don't hear them coming. So all of a sudden they're booming over you. It's really cool. So go to an air show someday. It's lots of fun. When we're allowed to do that again. Okay, so here is the final picture in here is showing some golden jacks, which are a type of fish. And they are riding the bow wave of this whale shark. So this whale shark is moving at a speed. It makes a bow wave. They're getting a free ride, and they're eating all the food before the whale shark can get it. Okay, all right. So that's the end of this section of chapter 19. Oh, I forgot something. I forgot to show you the Doppler effect in action. So hold on. Okay, I'm going to move this back and forth. And you might be able to hear it. Changing its frequency. So if you hear it go, woo, 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 that's the Doppler effect. Let me try the tuning fork all by itself. So if you hear kind of a buzzing sound, that's the Doppler effect with the tuning fork. Okay. That's the end.